Like for the first time ever, you have the ability to push the limits of intelligence itself and drive gains in how much energy you're using per task that you're doing there. So even though historically this has been only restrained to physical work, for the first time ever, you can actually push intelligence directly with advancements in the hardware and using the hardware better. So we call this intelligence per watt, which is basically how much energy are you using to get that unit of intelligence out to produce a result. The mission of our company is maximizing intelligence per watt.
Welcome back to Alexa's Input. For the last few years, the AI conversation has been dominated by more parameters, more GPUs, more data. But in 2026, the conversation has shifted to how. How do we actually run these models without melting the grid or bankrupting the enterprise? So today, our guest is at the epicenter of this shift. Emilio Andere is the co-founder and CEO of Wafer. With a background spanning the University of Chicago SAM Lab and Argonne National Laboratory, Emilio is now building what he calls autonomous performance engineers, AI agents that optimize the hardware to software bridge so that humans don't have to. We're going to dive into why inference and its optimization is a new frontier, the current AI hardware and inference landscape, and what it really takes to build intelligence per watt. So, Emilio, welcome to the show.
Thank you so much for having me, Alexa.
Thanks for coming. I'm really excited to have this discussion. So we spent 2 years, or the past 2 years, more or less, obsessed with things like flops and GPU counts. Other than, I would say, national labs and people that use HPC, which I've been obsessed with that for a while. But can you tell me, what does intelligent per watt actually mean, and why is it a good metric for a future of abundance?
Yeah, totally. So throughout history, if you look at civilizational progress, you always see a correlation between let's call like the average well-being of a human born on Earth. Just like out of every human born in a year, how many of them are above like the like well-being scale of just having enough food, having enough water, whatever it is. And you see this correlation between the average well-being in the world, which has been going up dramatically because of technology, and then the amount of energy harnessed and used by humans. So if you go all the way back to when we started with technology, just the wheel, whatever you want to call it, we've been finding more efficient ways to use energy in the physical world, all the way from, if you look at, again, I mentioned the wheel, all the way to like a nuclear power plant, right? And then if you look at the brain also is just energy consumption. Like you take in some sort of energy, let's call it calories, and then you produce some intelligence, some tasks that you can do with your brain to produce economic value. For the first time ever, when LLMs were invented, we passed the threshold where for some human activities, it was actually more worth it to just use an LLM over a human. What we refer this to is just like, for the first time ever, you have the ability to push the limits of intelligence itself and drive gains in sort of like how much energy you're using per task that you're doing there. So even though historically this has been only restrained to like physical work of just like, hey, I can harness more energy, I can do more stuff with the same amount of input, for the first time ever, you can actually push intelligence directly with advancements in just like the hardware and like using the hardware better. So we call this like intelligence per watt, which is basically how much energy are you using to get that unit of intelligence out to produce a result. And that's what the mission of our company is, maximizing intelligence per watt. We want to push intelligence per watt as high as possible so that you're extracting the most intelligence with the least energy.
That's fascinating, right? The idea of our brains as machines. But it's true, they use energy, and comparing it to how well the machines are running now. I just think that's a fascinating idea.
Yeah, you just kind of start to think about it as everything where like an LLM could do something for cheaper, intelligence-wise, than a human, will probably, just because of like efficient markets, be replaced with LLMs doing that. And there will be a ton of energy and cost consumption in doing so. And there's not enough people thinking about like how to actually make this more economical, because the more economical it is, the more things you can automate, and the faster you can just like have some sort of like economic growth from that. So yeah, that's why we're really excited about this.
And where do you think that line is right now?
I mean, it's a really good question. I don't know. I would say that we're about like, if I had to put an IQ to LLMs, which is hard because they're really good at some things that require like 150 IQ, and then they're really bad at some things which require like 80 IQ. I would say if I had to put a number, I'd put it at like I'd say it's at a point where it's like almost close to like the average human. So let's call it like 100. Um, I don't know if that's a hot take, but like I think most of our work is done with LLMs. Most smart people I talk to have told me the same. So that's where I'd put it.
So you mentioned something I like because I read your manifesto on your website on this book, Energy and Civilization, a History, and you kind of referenced it in your first
Yeah.
chapter. I have your manifesto here. So this is what I read on the Wafer manifesto. Your page says that every successful tool is a bet on efficiency. A water wheel grinds more grain per unit effort than a quern. A transistor switches more operations per watt than a vacuum tube. This civilization's pattern is do more work with less energy. For 10,000 years, efficiency meant physical work. Intellectual work rode the surplus. Better farming, manufacturing, transport. But the brain itself bottlenecked every intellectual task. Compute changes this. For the first time, we can drive efficiency gains in intellectual work directly. Any repeatable job with measurable output has an efficiency ratio. Useful work divided by energy consumed, intelligence per watt. Humans perform tasks at some quality rated outcomes per kilowatt hour. AI systems do the same jobs. We can measure both the same way. AI is crossing the human baseline domain after domain. The world's hardest problems are information problems, and human intelligence is no longer the limit. The cost of intelligence per unit energy is that limit. Every order of magnitude drop in cost expands the set of solvable problems. Our mission at Wafer is to maximize intelligence per watt by using AI to optimize AI infrastructure, achieving thousands of times better energy and cost efficiency. We believe cheap intelligence is the most essential piece of technology for a future of abundance. We will build the future intelligence too cheap to meter. The Wafer team. Okay, that was a long one, but I think that it's good context for people. But I liked in this you linked to this book, which I bought, but I haven't read yet. It's on my list. Right now I'm reading Count of Monte Cristo, which takes a while.
Nice.
Nice. So can you talk me through this a bit about how you came up with this manifesto, why you referenced this book? What does it mean to you?
Yeah, totally. It was me and my co-founder when we started the company. We were like, okay, what do we really care about and what do we want to work on? So we decided to work on this exact problem actually, and this is good context because it fulfilled three things for us. It fulfilled one is this something that we're uniquely equipped to solve, which we thought we were. The second one is this problem one of humanity's most important problems? And we were like, yeah, we think it is. And then the third one was, are we uniquely excited about being the ones to solve this problem? So that was like the third one, and it was in this case. So that was kind of like the background for starting the company. And then when we did, we were like, okay, how do we capture this into a mission that makes sense and that we can sort of like grow into as a company? And at U Chicago, when you take Energy and Civilization, which is the university that we both went to, both me and my co-founder, you have to read, like the first assigned reading is the book that we link here. One of the most useful things about the book is that it will basically, as you'll see, it basically just goes through literally the entire history of civilization from like when we invent like fire to the technologies that we've invented over like the industrial revolutions in like the past like 50 to 100 years. And it just runs through literally the numbers on like the efficiency gains and what are the consequences and second order effects of having those efficiency gains in unit of energy for the output of humans in all these different fields. Like what happened when we invented agriculture and what did that mean for like how much efficiency you need for like every calorie you consume. Now it's much faster to consume calories and like that efficiency has gone up. And he just goes through each of these examples, and we just thought it was like an extremely good starting point to think about like when is it worth it to optimize intelligence to just be much cheaper and be much faster, because at this point you can do these same calculations and say, hey, if let's just say like doing a presentation, just for like a silly example, if doing a slide costs me X units of energy and I can reduce that by like 10, let's say by a factor of 10, so I can do like X times 0.10 just to like get the percentage and get the like actual total of like my optimization, then now you can actually calculate all these like second order things. Like, okay, this is 10 times cheaper, therefore all these things could happen for the world. The TLDR of all this is that like Energy and Civilization provided a really good sort of like framework and background to think about these things of cheapifying intelligence as systematically as possible. And we just really liked it as a foundation for like how we thought about maximizing intelligence per watt.
Those three questions are pretty profound. Did you come up with them?
Yeah, we came up with them when we were listing out like what we wanted to work on, because there was a lot of stuff that fit two, but not three. And we just found the like little Venn diagram intersection of all three to be a very useful metric for us.
That's fascinating. So since we're on the topic, tell me a little bit about your journey and how you got here. You said one of the questions were, are we equipped to solve this? What about your history and what you had done made you feel yes about that?
So My co-founder is one of the smartest people I know. And he was one of those people that you're like, okay, at some point I would love to work with him. And then when we actually talked about it, it turned out that he wanted to do a startup now, which was great for me because I saw it as a potential future thing. But I'm very fortunate to like work with this person. The way we started is Steven and I have been friends for our first year, since our first year of college. We founded a couple clubs together. We did very different things, but we were both very interested in very technical topics and very challenging things. So I studied math at U Chicago, and most of my background was in AI research. So I did a lot of research on like predicting the weather using vision transformers. I did a lot of research on like ML security for protecting backdoors for machine learning models. So I did a lot of research in that sense. And then Steven came a lot from like the infrastructure background. So he worked at Google where he was doing infrastructure for what at the time was called Bard, but now is Gemini. He had worked at Two Sigma doing software engineering for their data center division. So he was doing a lot of work with like reliability of GPUs, just like measuring, like benchmarking, and doing a lot of work at Two Sigma in that. So he had a lot of the infrastructure background and he had seen the sort of like GPU utilization problem, which is like enterprises around the world have massive clusters of GPUs and very few people, even Two Sigma, very few people have the skills to make these GPUs run as efficiently as possible. At the same time, on the other side of the equation, I was doing AI research and I was writing a lot of just like PyTorch. I wasn't going down to like the kernels level, but I was often bottlenecked by how slow my model ran when I would run my model and I was experimenting with different architectures that just weren't part of like what NVIDIA had already hand optimized for those chips or what so you often found this bottleneck when if you use a regular transformer like the one everybody is using. Well, NVIDIA has spent a lot of time optimizing this already, so you'll get pretty good performance out of the box. But if you're a researcher and you're trying to do some novel architecture stuff, you'll find that actually your performance is really bad when you try to do some non-vanilla architecture that's very unique. Because, and this is kind of where the illusion breaks, the reason it's slow is because the NVIDIA engineers haven't hand optimized those kernels to be really fast for that model. So we kind of started talking about it, and that's where we sort of got to the conclusion that this thesis fit our three requirements that we needed, and we decided to start the company. But I came more from the AI background, Steven came more from like the infrastructure background, and that's the answer to why we were so uniquely fit to solve this exact problem, because we had both perspectives. And then we started Wafer.
So Wafer helps people optimize on top of the hardware.
Yeah, I can also talk a bit about wafers. What we basically do is we grab a model that's running, an AI model that's running on a GPU, an accelerator, like think of NVIDIA GPUs and AMD GPUs, but there's also many others coming along these days. There's Trainium from AWS. There's TPUs from Google. There's the really weird chips that are very cool, like Cerebras, like Sambanova. So there's all these like different ways to run AI models coming online. And in the other side of the equation, there's very few people in the world who can optimize these models to run efficiently on that hardware. So you have this crazy disbalance in the market where there's a huge demand for people that can write kernels and that can optimize models to run as fast as possible, what people call generally performance engineers. And there's also very few people that can do that work. So you'll see these people getting paid literally millions of dollars a year by companies like OpenAI, NVIDIA, Meta, etc., just for them to work on optimizing the models to run more efficiently on the hardware. And it makes economical sense because if they can optimize even 1%, that can save enterprises, especially large enterprises, millions of dollars. So what we're doing is saying, hey, to solve for this lack of supply in the market of human performance engineers, agents have gotten really good at coding and have gotten really good at doing this exact type of work. So what if we just optimize AI models to run as fast as possible with autonomous performance engineers? So these autonomous performance engineers will grab an LLM and will figure out ways to make it run faster on GPUs and on any of these hardwares so that you don't have to go hire the $1 million performance engineer. You can just use software to optimize these models to run as fast as possible. And that's what we've been working on for the past 8 months now.
And it sounds like it'll also make it easier for people to run their LMs on-prem.
Yeah, exactly. Because normally, like, you would have to go to all these inference providers. And I mean, we serve our own models and we're an inference provider, but we also tell people, like, hey, if you want to run on-prem, if you want to run on your own infrastructure, and you don't want to go to like all these companies that will just say, like, if you want the optimizations, you have to run with us, we can give you the agent that'll optimize your LLM and we'll keep it in your infrastructure. And then you can run it there. So you get the benefit of like a managed inference provider without having to go to a managed inference provider. Because as you know, there's many companies that simply can't because of compliance, because of all these different reasons.
When you see the layout now, on-prem, cloud, like major cloud providers, and then neocloud, how do you see that evolving?
It's a tough question. I think the the spend from hyperscalers is absurd, and it's hard to see a world where they don't end up dominating a lot of the compute spend in the world. So if you look at the tokens being spent, like I think it's like 50 to 65 or 70% of all tokens being spent are currently used mostly just by like OpenAI and Anthropic. And then the downstream effect of that is that they want compute. So they go to all these hyperscalers and they will like give them some capacity so that they can run their models and they can secure more gigawatts to run their specific models. In this case, let's say Opus 4.7 or GPT 5.5. So that seems to be driving a majority of the AI data center demand and people building out this insane infrastructure to serve OpenAI and Anthropic. But then you also see this other 30% that other people are running open source models, and those are growing a ton. You see the amount of billions of tokens processed by open source is growing massively every month, and more companies are turning to open source models for better reliability, better speeds, for compliance reasons, right? So there's kind of those two sides. So to answer your question directly, given those two things, I think because of the insane need for just people that can scale as fast as possible, I think the hyperscalers will grow like crazy. And this is not financial advice. I don't have anything in the stock market, but I would very bet on Amazon and all these Microsoft and all these companies that are doing these insane build outs. And then on the other side, I think these neoclouds will start consolidating into the classic, I forget the exact term, but it's when you have most of the market dominated by like a couple of people. I think you currently see like, if you look at the semi-analysis list and all the data center companies, there's like hundreds of data center companies. I think with time, those will start consolidating into the best ones, which seem to be like CoreWeave and like a couple others. Yeah, so it's hard to predict the future. I'm not sure, but it seems like the hyperscalers will continue to see massive growth while the neoclouds will consolidate into like less players that are just very, very strong and can start competing with the hyperscalers too in the next 5 years.
Yeah, and with compute, if it becomes easier to run and manage these, do you see them picking up in these on-prem companies that already have on-prem resources but aren't using it for LLMs yet, for example?
Yeah. So yeah, I didn't mention on-prem there at all. The on-prem is interesting because it seems like a lot of people that really care about like data security and compliance and like all these different very important aspects of running large companies really care about on-prem. I see like a lot of banks, a lot of every sort of financial institution, healthcare, all these places that literally just prefer to just go buy GPUs and run them on their own. I don't know exactly what will happen to that. And I mean, you worked at Bloomberg, so maybe you have a good perspective here. I would like to hear. I don't know. Like, what do you think? I have more of a perspective on the cloud side.
No, I'm also very curious. That's why I was asking you. I mean, from my perspective, these big bank type companies really want to own their hardware and they do have the resources for it, but I'm not sure which way it will go. That's why I was curious. We'll see. The way I'm working right now, I'm kind of hoping that more people want to run it on-prem and that we can optimize it, because that's what I'm trying to do. But I mean, we'll see. This is interesting to me. Can we take a step back and can you walk me through the GPU hardware landscape and how we got here?
Really interesting market. I'm going to say the perspective of a startup and what it's like to be a startup that needs a lot of GPUs. What you see, because I think that's the most interesting one because it's the one that I have the most direct experience in. I think a lot of our time is spent trying to secure GPUs and trying to actually get compute at decent prices. I think for the past month, it's been impossible basically to get any Blackwell GPUs at decent prices that are not on insane commitments of 3 to 5 year commitments, which as a startup is impossible to make.
So for the listener, Blackwell, those are the E200 GPUs, right? So can you maybe walk me through the different landscape of GPUs before you go into that?
Yeah, totally. Okay. So when you're trying to buy GPUs, you'll see when you're trying to buy data center GPUs, which is where most people run LLMs today for inference, you'll see that there's basically only two players. And there's a caveat there, but there's basically only two players where you can buy. It's basically NVIDIA and AMD. So the latest NVIDIA hardware that's actually online are Blackwell GPUs. The previous ones were Hopper, which were extremely successful, the H100 and the H200, which a lot of people have heard about. Now, NVIDIA has been releasing Blackwell for a couple of years now. And Blackwell, you'll see as B200s, B300s, and you'll also see a GB for when there's also a CPU included here. So it'll be GB. And there's extremely high demand for these GPUs right now. You'll see that if you look at the indexes for these GPUs, you'll see that the price has increased from, I think 6 months ago, we were at $4 per GPU hour for Blackwell for both B200 and let's just call it B200s to compare sort of like apples to apples. And then if you look at it right now, we've gone up to like 650 or around that price range for the same GPU node, just because of the insane increase in demand that there are for these GPUs. So that's like 90% of the market and that NVIDIA owns.
Each of those GPUs have different uses, right? They have different stats and different reasons why you would prefer one over the other.
Yeah, exactly. So Blackwell is, to be honest, most of the, if you go look at artificial analysis or all these leaderboards that show LLMs running at what speeds, most of them today are running on NVIDIA Blackwells. If you're trying to run inference, they are out of the box. If you're trying to put the least effort into optimizing that inference, the fastest you will get. So that's the use case that a lot of people are using them, but also Blackwells are really, really good for training.
Why are they the fastest? What about NVIDIA makes them so great?
Yeah, so it's their software. If you actually look at the hardware, AMD MI355, which is the competitor to Blackwell's, so to speak, from the AMD side, actually has more memory, which is the thing that would make you go faster, right? But in the case of NVIDIA as an estimate has like 4,000, maybe close to 5,000 CUDA engineers that are literally spending all their time manually optimizing the code that lives on top of the GPU to run extremely fast. And if you look at a company like AMD, which is a great company, but is like just realistically like a tenth the market size as NVIDIA, they don't have as many resources to invest into the software side. And they have changed this very recently, and they're doing great efforts to increase the capacity that they put into making the software faster. But yeah, just the short answer to your question is just it's a software problem because their hardwares are comparable at like the exact just hardware numbers.
That's fascinating.
Yeah.
But AMD is another big competitor.
AMD is a big competitor that's been growing. AMD is, I would say, the estimates aren't super clear, but I think it's like I would say I would put it at like 6% of the market right now in terms of data center GPUs, and NVIDIA is like 90%. So AMD has been growing that and has, I think the projections are super positive for how AMD will grow in the next couple of years. They had this big deal with Meta for powering a lot of their LLM usage. The rumors are, this hasn't been officially announced, but there's a lot of rumors that they have a big deal with Anthropic. So Anthropic maybe will start using them. OpenAI, of course, had, I think what was it? Like, it was one of those crazy AI deals where they invested in AMD and now own 10% of the companies, something like that, or the other way around. Yeah, AMD is definitely growing, but there's a lot of room to improve, which is a lot of the stuff that we work on.
And who is trailing after them?
Yeah, so trailing after them is now a bunch of people, all the way from the earliest startups to startups that have been in the game for long. So the most common ones you'll hear are companies like Cerebras, which is gonna IPO, and they've been doing a great job at wafer scale chips. So they basically say, hey, most of the bottleneck in running these LLMs is communication. So what if we just make a humongous chip where we can fit the entire model or close to the entire model, which is a crazy idea. And it's an insane accomplishment from Cerebras that they made it work. And I'm excited to see how they do. And they've been doing really great. And then Trainium is another one from AWS. And the perspective on AWS that I have is that they're really good at cheapifying things that already exist. They did this with x86. They basically created Graviton, which was their own version of to cheapify the chip and compete with Intel. And they did a really good job on that side, and they ended up taking a lot of that market just from having a cheaper version. So I'm quite bullish on AWS being able to grab whatever NVIDIA does and just make a cheaper version of it that's as good or almost as good. So I'm very excited about Trainium personally. And then the other one I have to mention just before I finish this is TPU from Google, because they've been doing a great job. They are really, really focused now on inference from what it seems like from the last release of V8. The story of TPUs, as I've learned, is a story of just a lot of lack of focus on the inference specifically. There were a lot of push from other parts of Google to use it for ads, for other stuff. But recently, there's been a huge push from Google internally, at least it seems like there's an external party here, to really focus the chip on just inference. And you see that with the latest chip where they just divided it into two different chips so that they can focus one completely on inference. So those are kind of like the main players in the game right now.
So how does TPU compare to the GPUs?
A TPU, in terms of performance, theoretically, okay, so the problem is, and the reason I'm struggling with this question is because there's kind of like the theoretical thing, which is TPUs in theory give you similar performance to a GPU. But on the other hand, another part of my brain is also like, there's actually very little public benchmarks about like GPUs versus TPUs. So Google doesn't submit the top benchmark in the world, which is MLPerf. And MLPerf is basically a benchmark where NVIDIA and AMD, like most of the submissions are just NVIDIA, will basically grab their chip and they will basically run a model with it, let's say for ease, Llama 3. And then they'll say, this is the performance that you get on this chip. And NVIDIA is most of the submissions. AMD is now submitting. And this is like, if you really want an apples to apples comparison, you would have to go look at like these benchmarks that are super rigorous and say, hey, here's how TPU compares. If we don't have that, we kind of just have like marketing materials from Google, which makes it kind of tough. And then I know Anthropic uses them a lot, so they might be getting good performance. But yeah, the data is not super clear. In theory, I will say you're supposed to get similar performance from a TPU than a GPU.
How hard is it to buy a TPU? Is Google the only person manufacturing TPUs?
Yes, Google is the only person manufacturing TPUs. This might not be true anymore as they're shipping TPUs to Anthropic. Historically, they've been the only one to manufacture these. Now they're sending like the actual boxes to Anthropic. So for the first time, they're actually making TPUs that will not go directly to GCP. In terms of how hard it is to get TPUs, it depends on the model version. It's relatively straightforward to get V6, which are 3-4 years ago, outdated by 3 or 4 years, maybe a bit more. It's possible to get V7 through GCP. V8 hasn't come out yet. So yeah, I'd say it's possible to get V7. It's possible to get some V7s, like a small number of nodes. But if you actually want to run scale inference on TPUs, that's a whole other sort of like thing that you have to go through, because most of the allocation goes to GCP to resell, and the other part of the allocation goes to internal teams at Google, and some small part is reserved for startups and people like us that want to try it out. But you can get it. It's just hard to get it at scale.
Is there a like third-party marketplace for GPU type of thing?
Yeah, you're kind of there's a ton of the market is kind of weird. There's people in the middle that will connect you to data center companies. Like people often call these like marketplaces or brokerage firms. Where I'll basically go to you, the brokerage firm, and say like, hey, I need this amount of Blackwell GPUs, like the NVIDIA B200. Can you find me someone that will give me this? And they will go through their network and try to find someone that has that capacity. And then the game ends up being super relationship focused and just very, I don't know what to call it, but it's not very fair. If you have a previous relationship with the brokerage or with the data center, you'll get preferential treatment. Yeah, there's many, many things, but it generally prefers the big players. Like if I build a data center with 100 GPUs, it's much less overhead for me as the data center to just rent out the 100 GPUs to one person, because it's just one person I have to deal with, versus renting one GPU to 100 people, because now it's 100 accounts I have to deal with. So when I go and tell them we need one node, and then another big customer is like, we need 500 nodes, they're like, oh, we don't have any GPUs. They do have them. They just don't want to give them to me because of the overhead of managing that. So it's a complicated game. It's pretty fun, but it's just a lot of nuances.
So now that we've got a good background of what there is in the market, can you tell me a bit more about the economics of it all?
Yeah. So, I mean, the economics of the neocloud are pretty straightforward. you will basically just you buy compute, and compute is traditionally a slightly depreciated asset. We're in a weird market where an H100 right now costs the same or more than it cost 4 years ago. This I don't know how to explain. I don't think anyone has really explained it very well, apart from just like there's insane demand. We don't know what's going on. But normally you buy an H100, and let's say you buy it for $100. Um, and that H100 will be useful for about 4 years. So now now you have to figure out, given that I just spent $100, how do I make this profitable over the 4 years that this H100 is good for? So let's say that it is $100 for 4 years. So then each year, your cost of one H100 in this example is $25. So now for those $25, I can say, well, let me sign a customer, and because I'll do the build out and because I'll manage the H100 for them, I will add a 10% margin on top. So I will charge them, instead of the $25 per year, I will charge them $27.5 per year. And now you have a 10% margin on your product. And this is basically a very simplified example of how it works, but that's basically how neoclouds just do the business. You just buy an asset, you divide it over the years that it'll be useful, and then you add a margin on top to make that, to like be able to resell that. So that's the lowest level of the stack. I didn't do anything to the GPU. I'm literally just giving you the bare metal GPU. And then when you look at higher levels of the stack, and if you look at the industry where it is today, every company, like every data center company, like CoreWeave, like Nebius, like all these data center companies want to go up like higher level of the stack. Well, they want to serve managed inference. They want to do all these like higher level stuff because that has better margin. Like that's just like the useful way of understanding this market. If I just go do the whole thing with H100 that I just outlined, my margin will be like 10%. And this is realistic. If you just sell the bare metal GPU, I bought it, I resold it to you, that's like 10 to 20% margin. But if I am like Base 10 or like one of these inference companies, and I, instead of just reselling you the GPU, tell you, hey, I bought this GPU for $100, it cost me $25 a year, but I have done some optimizations on top of the GPU where I'm not just going to give you the box. I'm just going to give you an endpoint with an LLM to call. And I'm going to assure you have 99.99 reliability. I'm going to assure you have this performance every second that you run it. All these different things that you have to ensure. Now, instead of telling you I'm giving you a 10% margin or I'm keeping a 10% margin, you can realistically go to softer margins, which are like 50 to 80% margins. And this is the margins that companies like Fireworks, Together, Based on have. So a lot of companies, like data center companies like CoreWeave, like Nebius, the ones I mentioned, they are trying to fight to go to that level of the stack, so they don't have to fight for the 10 to 20% margins and can instead be at like the 50 to 80% margins. And like a ton of acquisitions going on in the space with these data center companies buying software companies to be able to go into that stack. So that's kind of like how the game works, from bare metal to like managed inference at all levels.
I want to go into the different type of optimizations that would lead to that. But first, something you mentioned earlier is that Google was giving or selling TPUs to Anthropic. And Anthropic would seem to be a competitor. What's going on and what is it leading to, you think?
This one's complicated because I think a lot of people are talking about a potential AI bubble. I think the like very reference thing that I hear is that of the dot-com bubble and how people overbuilt fiber cables, and then there wasn't an actual need for it. So then by the time all these fiber cables were built out, everybody was kind of left in the dust without like the usage that they were expecting. I think the counter argument that's very convincing that I've heard is that with GPUs, if you look at NVIDIA, if you look at AMD, they are basically sold out for the next 5 years. So it's an interesting structure where, okay, it might be a bubble, but also it seems materially different than what people have been talking about historically of bubbles, where there's a risk that in the future, there's not the demand that people are showing today with their money, because there's so much demand for these GPUs that people are taking on 5-year contracts just to get access to them today. And there's a whole situation in which, like, if their revenues don't go up, they might have to default on those contracts. And what will happen then? And like, what's the bubble then? And that's an interesting conversation. I would say that like I'm generally biased towards the this is not a bubble because of how useful it is to the smartest people I know and how useful it is to us and how I've seen organizations just adopt these tools, and I think it could lead to massive increases in revenue. But again, I'm 23 years old. I don't want to try to predict the future too much.
The crazy thing that you mentioned is that they're sold out for the next 5 years. And think about how much AI has changed in the last 2.5 years. The idea that they are completely sold out for the next 5 years is crazy. Like, why is that?
It's crazy. No, it's crazy. I mean, pair that with the fact that if you bought an H100 4 years ago, today it would be worth more money. Zero depreciating asset. It just did not go down in value. Think about a car. The moment you get it out of the dealership, you lose like 30% of the value or whatever it is. An H100 has maintained the value through 4 years. Plus what you said of just the commitments of up to 5 years. It's a crazy market. I'm not going to try and say I fully understand it. My observation here is that there just seems to be an insatiable demand at the moment for just running these models and adopting them as fast as possible. And it'll be interesting to see what the next 2 years holds, not even 5, because as you said, like think about where we were 2 to 3 years ago with AI. I don't know that anyone could have predicted the like rise of what we see today of these like fully autonomous agents doing all these things. Yeah, I mean it's very interesting. I'm excited for it, but yeah, we'll see how it goes.
And something that could disrupt this, which leads us into the next thing I wanted to talk to you about, are all the different optimizations that are on top of this stack. So people are trying to optimize above the hardware to make better use of the hardware. I know that traditionally GPUs notoriously have a reputation for having something like 20% utilization as well. What are all the different types of optimizations that people are working on above this layer of the hardware?
Yeah, totally. So this is a fascinating topic. And I'll just do like the super simple high level overview. There's a couple of spaces where you like, let's say you just have an LLM. Let's say Llama 3 came out and you're just a company and you're just like looking at the weights, you're looking at the architecture, you're like, okay, this is what I have, this is where I could run it. You'll see that most people will just grab the LLM and start up the LLM, start up SGLang, and then we'll just like run it. And that'll give you like a decent utilization because VLLM and SGLang are amazing projects that thousands of people have done like contributions for.
Yeah,
Now,
I do. I was trying to get my contribution in and I couldn't because everyone kept merging. That repo has an amazing amount of contributions to it.
it's crazy, right?
Yeah.
It's crazy. And then the amount of things happening every time you try to merge something, you're just outdated immediately because there's like another 10 people doing similar stuff. Yeah. So you run it with VLLM, but let's say you're part of this large set of companies that really, really care about either compliance or speed or cost. So if you really care about speed or cost, you'll really optimize for how do I grab the model that's running today and make it run faster. So most people will start at the inference engine level. And you'll see that like VLLM and all these different inference engines have a ton of flags to go through to make your model run efficiently. It's just literally like a hyperparameter search, which you could spend mathematically like millions of years in, but you find optimal ways to search through it as you do in many types of hyperparameter searches. The way we do it is through an agent that tries the different flags, checks to see if it's actually faster, and then repeats with all these different flags. But independently of that, the way a human will do it, you'll just sit down and you'll just tweak these things. Like, hey, what if my batch size is this? What if my context length is this? What if my like everything that you can think of to run an LLM? What if my KV cache utilization is this? So that's sort of like the first lever you'll pull to get the best performance from the lowest hanging fruit. Then once you get there, you can do two other things that this is what most people do. The second thing is, depending on if you can sacrifice a bit of quality, you'll do something called quantization. And quantization will basically be, hey, every weight is represented with a number of bytes. What if we just reduce those bytes so that the weights are represented with less numbers? So if you look at a trained LLM, it'll just be like millions of numbers that are the weights, and those weights will be represented with some accuracy. So I can represent the weights with, if let's say that instead of representing them with 4 numbers, like 3.1415, I instead just want to store it as three numbers, 3.14 or 3.1 for two numbers. I have reduced the size of every one of my weights by 50% if I go from 4 to 2. So now loading the model and running inference takes not exactly half, but like a lot less because every weight is just less information. So that's one way of reducing. And you can apply quantization through a lot of parts of the model.
Is that output after that?
The impact is that you end up with a dumber model. In the average case, if you're very careful, you can actually have near lossless quantization that gives you almost 2x the performance or more, depending on how far you're going with like reducing the amount of bytes. Gives you, yeah, like massive speeds and performance without reducing as much quality. And it also depends on your use case. This is also why it's useful to have just like people or agents that really know about like what you're using the LLM for. Because it's just like, hey, if you're using it for, what do we call it? Maybe like a very simple application. Let's say like some sort of like summarization chatbot that just grabs a document and summarizes it. It's fine if we lose like some percentage of accuracy on how smart the model is, because summarization is generally like a pretty solved task with like most good LLMs. But if you're doing like frontier level mathematics and you want to use the best models, then you really don't want to quantize, because like every drop, even if small in accuracy, just like, is less of a chance that you'll get to the solution. So it depends on your use case. And this is something that we work on with customers to just figure out where we want to pull the levers. So
Something in software engineering that has been shown through time. I mean, and as each of these tools or components has evolved, there have been less differences in, needing to know which one you need for a use case, but like coding languages, for example, and also databases. And I think that's something that has always been a very use case specific tool until they've been optimized to a point where sometimes it doesn't matter. But I think we're eating the same type of thing now, but people maybe just aren't as familiar because it's so new about where they can lose that accuracy.
I think that's right. I think that's right. So we're in a weird sort of like in between where you still kind of need like a person that really knows, and you need to test very carefully to like, if you really care about specific use case, run these evals to know that we haven't sacrificed a lot of quality. But yeah, it's an interesting game that a lot of gains can come from just having an agent also try this, which we also work on. The other aspect that I wanted to talk about that is very sort of like talked about these days is having a smaller model that predicts the output tokens of the bigger model. This is commonly called speculative decoding. Also, when you do it without a separate model and you instead do it within the same model, it's called MTP, multi-token prediction. So these are the two ways which you can use a smaller model to predict some tokens ahead. So because the LLM instead doesn't have to generate the next tokens, it's just verifying that the ones that the small model generated are correct. And that can also give you massive speedups. And a lot of people are trying this out and are very excited by this.
In what use cases do you get massive speedups from running another small model?
There's the use cases where the output tokens are most similar to each other, like the patterns are very specific. So the most common one is coding. With coding, you'll have like a lot of the data is like within some sort of like distribution of how it looks. Because if you have an agent that's just really, really good at writing Python, most Python can boil down to, I don't know if 100, but maybe 1,000 operators that you just choose on keywords like def, like all these different tokens that you use. Therefore, because it's more predictable, a speculative decoding model will have what you call a higher acceptance rate, which is the bigger model will accept and average more of the tokens that the smaller model predicts. And that can give you massive speedups, because if you use the smaller model to predict the next three tokens and the next model accepts all three, that's a very different sort of optimization and much stronger than if the model only accepts the first one and then rejects the second two because there was some time wasted in the second two. So yeah, I think a lot of people are very excited about a spec decode, and it's very worthwhile, and it's something that we're really looking into.
So, what are the bottlenecks that these are solving for? Is it bandwidth, memory? Each of them seem to have different bottlenecks. Which one are the top bottlenecks that these are solving for?
Quantization will really help with like moving memory around because it's very expensive. Most of these GPUs are not really compute bound anymore. Like we figured out how to put a lot of compute units into this GPU so you can do a lot of like matrix multiply at the same time. But the most expensive part with GPUs and why they are often slow and why the code that runs on them is often slow is because they are often memory bound, which is like I have to move data from this part to this part, and that's a very slow process, and that's dominating the time it's taking to do like the inference or the training. So quantization will help because if you can reduce the size of the weights by half, then you only have to move half the data. So that's really helpful for memory bound problems.
Be clear, every time you receive tokens, you're creating these weights.
Yeah, exactly. So there's some nuances with like caches, KB cache, and these different things, but I think in general that's a very useful heuristic of just like, yeah, every time you receive these tokens, you have to process them and move them around to be able to do inference.
And then you have to generate them as well.
And then you have to generate them. So this is when you look at like LLMs, as we know, they are autoregressive. So you're looking at the previous sequence to generate one more token at a time. And this is very bound on memory because you're looking through all your previous tokens. Again, the nuance here is KB cache, but in the most simplified example, you're looking back at all your tokens to compute the sort of like the new attention, the new KV for the new token to be able to output the result. So that is commonly also just like spec decoding helps a lot with this because your verification is much cheaper than generation. So if you have a smaller model generating it, you can save a lot on the resources of generating from the big model. And then there's also faster kernels, but that's a separate topic. For spec decode and quantization, that's generally what it targets.
It seems like there are two things that it's solving for here, latency and cost. But where are those bottlenecks? Where do you have to compare and choose one there?
Yeah, I think when we ask customers, like, what do you really care about, latency or cost? They just say both. There's ways there's ways to like change it up so that you can optimize for both. You can actually, in a lot of cases, you can just pay more money to get better latency. And that's a fine trade-off that you can make with most models because, for example, I'm not sure if you use Claude Code, but they have like a fast mode. That fast mode is really expensive. And the reason it's very expensive is because they're literally just putting you in a different GPU that has lower batch size so that they can literally just make much less money on every user request because there's less users per GPU. So they'll trade off costs and just say, hey, you can pay more. Therefore, you can get all these latency gains. So it is kind of like you can pull from both sides. And then there's a sort of like Pareto frontier of just like, here is how far you can get in each of those dimensions while balancing them out. But it is a trade-off.
So we have all these different mechanisms. Like I know there are semantic routing mechanisms, ways to route to the GPU that has the cache, different ways to transfer the memory, different ways to quantize to make that faster. Of all these components, what do you feel like we're still missing?
I think there's a lot of research to be done, and I'm pretty biased here on how do you run these models well on hardware that is not very common and hardware that not a lot of people are optimizing for. So again, I said I'm very biased here because this is what like our company does. But given that it can run well on a GPU, on NVIDIA GPU, that doesn't mean it can run well on an AMD GPU or on Trainium or on TPU. So how do you rewrite the code so that it runs well on every one of these devices? It's just an important question that we think about all the time and not a lot of people are thinking about. A lot of people are either invested by NVIDIA directly, so they're not incentivized to use other providers. They just really like NVIDIA because it gives them good performance out of the box. So we're in this space where NVIDIA has 90% margins on every one of their GPUs. And it's simply because not enough people are thinking about like, what if we had a second option that was as good? And what needs to happen to have that second option? And what would be the impact on like the price for the market? Because a very reasonable statement is that if you really care about maximizing like intelligence per watt, then like one of the ways that you can reduce the spend and like the watts is just by like having alternatives. So the market can be more intelligent and actually make a decision on which one they prefer. So I think very close to hardware level optimizations are often ignored because they're very hard and very boring to a lot of people. But I think they will end up being one of the most important research areas to work on in the next couple of years because of what I'm talking about. It opens up the opportunity to use other hardwares that are not NVIDIA.
And a lot of these tools are fairly new, like the usage of KV cache and VLM and LMD and these quantization things, where do you think there can be the most improvement in these certain parts of the optimizations too?
Yeah, I think, okay, so this is a really good question. I think VLLM is at a point where it's really good. Arbitrary company can run an LLM with VLLM and get decent performance out of the table. I think with a lot of other projects that are newer, there's a lot of work to be done. So for example, all the Dynamo-like tools that orchestrate across multiple nodes to do large scale inference. There's a lot of great work that NVIDIA has done here, but there's a lot of work that needs to be done in making it more usable for people. It's really hard, even for us that we would be in the category of like highly technical because we're like a small startup with only like engineers. Even for us, kind of gets complicated to run Dynamo and all these large scale orchestration platforms. I think tools that have withstood the test of time, like Kubernetes, like Docker, are doing an amazing job in the AI world, and they've been prepared for this world. But all these newer tools, like Dynamo and the competitors that are more open source, is one example where I'm excited to see improvements. That's the one area that came to mind. There's probably more, but yeah, that's the one.
You mentioned that the neoclouds want to have higher abstraction to basically become a cloud. You have like a model as a service or an LLM as a
hmm
service type thing.
hmm
So what does it take to create a platform like that?
A lot, a lot, and that's why you see a lot of investment from the data centers that I mentioned to really scale up that service. So the one recent example here that might be relevant is that like about a week ago, Nebius bought a company called EigenAI, that was like a managed inference provider that was a year old for like 640 million. And it's basically, they were a team that didn't know much about the infrastructure side of things on building out data centers, but they really knew about just software and how to make the orchestration layer, the optimizations just run as fast as possible and just run reliably. So generally, I would say there's a couple of things here. The first thing is you have some notion of reliability. And enterprises really, really care about reliability, which is okay, how many nines of reliability can you tell me that this service will be up? And that's a huge lever to pull. And companies there's entire companies just dedicated to maximum reliability for LLM serving. Then the second one that people care about is speed. How much performance can you give me out of this LLM so that I can run it in prod and at what speed? So they'll ask about that. And so you have reliability and you have speed. And then the third one that people really care about is cost, which is given that GPUs are very expensive and given that I'm going to be spending all this money, how do I make sure that I have the best price while still balancing good reliability with good speed? Those are kind of the three sort of, at least in my experience from talking to these companies and from reading about this, there seems to be a massive focus on these three. In terms of how you
They worry about like how secure is it to all be using the same models running?
Yeah. So I was focusing on like dedicated endpoints where they have the full box for themselves. And I was putting that a bit into reliability, but I think security is important we can distinguish that into a fourth one, security, because a lot of people care about what's your data retention. Are you like HIPAA? Are you SOC 2? All these like very important questions for large enterprises. So yeah, security is also an important one. So then in terms of like the reliability, what you have to build out to get good reliability as an inference provider is just a really good orchestration layer and a really good like routing layer so that when something fails, you are just like extremely prepared for that situation, because with GPUs, something will fail. Like I'm sure you've experienced this too, but it's just like GPUs are extremely faulty machines, and like even if they are good, let's just say 1 in 1,000 works, when you have massive deployments, that still ends up being like a lot more than the nines of reliability that you want to promise to be competitive in this space. Um, so we put a lot of focus into how do we orchestrate our engines? How do we orchestrate our GPUs so that if something is down, we can immediately reroute to a GPU that is up so that the end customer never sees any signal of downtime. And there's a ton of more things to say on reliability, but that's the first aspect. The second thing is speed, which is something that I would say is our specialty, which is how do you grab the model that exists today? And with all the strategies that we talked about that I won't repeat here again, but with all the strategies that we talked about previously, how do you make that model go faster? And people, they will compare you against other providers. They will say, this provider gives me X, can you give me X? And this will be a game of just like, can you get the fastest speeds? And the hard part about speed is that they also want cost, which is what we were talking about before of like latency versus cost. People want the fastest speeds at the cheapest prices. So it's an interesting game where you also have to figure out, okay, there's a metric called total cost of ownership. Given the hardware that I'm going to use, what is a good balance between how fast I can go and how much that hardware is going to cost me? Like I could go to a customer and charge them, I don't know, like charge them X what I'm supposed to charge them to give them a lot more performance, but I'm not really going to be competitive with other people who are charging them half of that for at least some notion of good performance that's like comparable. You have to balance these two. When you actually build these out, it comes down to orchestration and optimization and just like figuring out like your hardware costs and how to choose the right hardware for the right job.
These systems can be highly distributed, not just inference across nodes, but also disaggregated, pre-filled, decode running on different GPUs or different hardware, and a lot of communication there. It seems like you need a lot of throughput for that, to have all of those optimizations for that to be useful, or at some point, it probably also slows you down, right? So how do you balance between running and managing all of that highly distributed software and also being fast and cheap?
Yeah. It's I mean it's a tough problem. I think there's a lot to do in terms of I mean the specific way we handle it is we just use cheaper hardware. So a Blackwell I told you is like 650 right now. We get AMD for like 270 or 280. That's not the exact price, but it's like just like a range. So like if you can have all these optimizations and you can get AMD to be 80% or 100% as efficient, then you have this advantage because it's just much cheaper to run your hardware.
So you're betting the software optimizations will outperform the hardware optimizations.
Yeah, because the hardware, if you just take the flops, how much the hardware can already give you, theoretically, it's already comparable to NVIDIA. It's literally just a software problem.
Another thing I saw on the Wafer website was something called Kernel Arena. Can you talk to me a bit about that tool?
Yeah, totally. So Kernel Arena is a way to benchmark how good are LLMs at generating kernels. So a kernel is just a piece of code that runs on a GPU. Kernels will basically determine how fast your AI model runs because everything that runs, everything, like when you define a model, let's say you write it in PyTorch, it'll be at the end of the day converted to kernels that run on a GPU. Like most of the model execution will be converted into code that runs on a GPU. So the idea is a lot of people are trying to optimize kernels to run as fast as possible. How do you actually systematically measure how good these LLMs are at doing so? And there's previous attempts to do so. And there's research background that led to this. For example, Kernel Bench is the foundational paper in the field. But we figured that a lot of the actual kernels that people use in production were not represented in those academic benchmarks. So we needed a more real benchmark of given these kernels that people use, that people are actually using for the latest open source models, let's measure how good LLMs are optimizing these kernels.
And what have you found from this? What are the major ways that they optimize?
Yeah. So in the case of Kernel Arena, the main way that they optimize is simply by like rewriting the code to utilize the hardware better. So that's like the main lever of optimization. And there's a whole subset of things you can do in like rewriting the code to make it work better. One of the main things is something that people call kernel fusion, which is basically instead of doing multiple separate operations where you move data from CPU to GPU, let's say you have to do like multiply. Instead of doing add, move the data to GPU, add, then move it back to CPU, then move it back to GPU and multiply, then move it back. Instead, you recognize that you're going to operate on the same data for those add and multiplies. So you do send it to the GPU once, add, multiply, both on the GPU, and then send it back at the end. That's called a fusion because you just fuse two operations into one. That's a very common way to do optimization for kernels. So there's many things like this that's just been.
How does this work with open weight models that you're using? Are you changing the actual model serving runtime, or how does that work?
Yeah, you are changing the runtime. VLLM and SGLang come preloaded with specific kernels to run specific models. So you're basically saying, hey, given the profile that I'm looking at, given the specific functionality that I'm trying to achieve, the stock image, the stock kernel that VLM gives me can be further optimized to this performance if you rewrite that code. So you'll do something called monkey patching, which is basically I will give you my own kernel instead of VLLM's kernel so that you at the end of the day are just running VLLM, but I'm just defining that instead of running this specific kernel for this specific part of the model, you're running my own kernel that I wrote.
And that's the main way you would say that Wafer best optimizes these LMs.
I would say we've had a lot of gains from kernels, and it was the initial focus of the company. I would also say that with time, we've ended up focusing a lot more on not just kernels, but also the higher levels of the stack, like things I mentioned. How do you quantize well without losing accuracy? How do you run like a speculative decoding model? And how do you train that model to be really good at predicting next tokens? We now, even though before we described ourselves as very kernel focused, we now describe ourselves as end-to-end model optimizers. And kernels is one of those strategies to get there, but there's many more now.
Have you found any results from these tests that have surprised you?
Yeah, I mean, there's a ton of things that have surprised us. I mean, one of our most shocking results was actually pretty recently when we were able to optimize Quen 3.6, be one of the latest Quens, to the number one spot in performance compared to all other providers on artificial analysis, purely on AMD hardware, which we think is the first ever like time that like AMD hardware would be like number one on that leaderboard because it's so dominated by NVIDIA. And to be honest, like I knew that this was like theoretically possible, but I had never seen it like done in like production and like to a real model. And one of our engineers who's brilliant like did this end to end and with the agent, and I was just very shocked by this. There's many more results like this in both NVIDIA and AMD, but this is one that we published like last week or this week actually earlier that I was just really, really excited by.
Are there any that you've been a bit disappointed by that have been really hyped up but not met the hype?
Yeah, I mean, I think there's always these, and I don't know if you saw the whole Twitter going crazy over Turbo Quant. And then like Turbo Quant was fine. I don't think it actually changed anything for us. The thing I'll say here is that not to like put down specific projects because every bit of effort counts to squeezing more performance out of LLMs. So I'll just say that in general, it's very hard to compare, as LLMs like to say, like apples to apples again. It's very hard to compare apples to apples in performance. And like people will often accidentally compare, let's just call it apples to oranges to continue that. It's you have to normalize so many things. You have to be very strict with profiling and benchmarking. I would say benchmarking is one of the hardest problems in like the area of just like machine learning systems and just like performance because there could be so many ways to get it wrong. So I think one of the most disappointing things is stuff that we didn't end up publishing, but that we were very excited about. And then at the end, we realized that we were just wrong. And our whole like week's effort was just like wrong because like a single piece of code in like our profiling and benchmarking script was, I'll just say an example, like not cleaning the cache properly. So times were underrepresented. Well, it's just a very hard problem.
But I like that you have that much attention onto it because benchmarking is very dependent on, all of the parameters. And I think that it's a call out to people also to make sure when you're looking at a benchmark, to make sure that you also check what were the parameters and how it was ran to, make sure that it's useful for you. It's really easy to make those small mistakes.
Exactly. Yeah, this is the stuff we were very careful with because it could be very, for the people that really know and the people that really pay attention, it could be very hurting to your reputation to be untruthful or even accidentally untruthful because you didn't know. People are very strict about this, so we're very careful about it.
So this is your first time being a founder. What is your biggest learning lesson? This is your first time being a founder. I'm sure you've learned a couple of lessons. What are a couple of things top of mind for you that you've learned?
I think the first thing that comes to mind is how different real sales is than what's portrayed in like Hollywood and just like what you think it could be or it would be. I've realized that sales is just being at the correct time and just being helpful to people and then basically without expecting anything in return. And then at some point you have something that actually fits the exact thing that person is looking for. And you're just like the person because they trust you, because they know you for whatever reason, you're just there to help. But I've generally have this perspective that I thought selling was kind of like the TV shows like Mad Men or like whatever it is of just like create this insane marketing, just have all these ideas, but then they kind of get thrown out the window the moment you actually try to sell something. And you're not trying to convince anyone to buy your products. You're just learning from people. And if you have the right product, then you say you should fairly compare it against everyone else. If you don't, then it's simply not a fit and you should just use it as feedback to just either improve in that direction or it's not a fit at the moment. So I think that's a long way of saying that sales is very different from what people put it out to be in this fantasized world. And it's just about helping people wherever you can and providing value. The other thing is that it's very much so an emotional roller coaster. And you have to regulate how much it affects your emotions. Because at the beginning, if a deal is not going through, for example, you feel very miserable personally. And then with time, you kind of get used to it and you learn to detach yourself in a healthy way, detach yourself a bit from the outcome. And just if it happens, I'll do everything in my power to make it happen. If it doesn't happen, I'll learn from it and improve for next time. But this shouldn't affect my well-being today. And it's something that I talk about with my co-founder a lot, because in the early days, your entire focus is how do I grow revenue? How do I create a value? How do I do these things? Those are the two things that come to mind. There's so many.
Could imagine. At this point, what do you consider the most challenging parts of your job?
I think the most challenging parts is you have this growing thing. You have this product that you want to grow. And as you grow the company, we're still pretty small. We're like 6 people. But as you grow the company, you are in a room with a bunch of smart people who have different opinions about things. And figuring out how to agree or disagree and then move on to action is, I think, one of the hardest parts of the job that I feel like personally, because you could have very smart people that just sit in a room and talk about the different options for like 12 hours. That's possible and you could do it, especially smart people that are good at talking. You'll just have this conversation that could be productive, but I think there's a decrease in your actual returns as the conversation goes on when you're trading it off against doing something and just finding information. So we're very biased towards action, and we really mean that in the sense that when we don't know what to do, we'll just do something and then take information from that action and then learn from it to be able to do something better next time if it was not the optimal thing. But basically, we live under the belief, and it's been very hard to learn this, live under the belief that action just produces information and you just have to go do something to see what will happen. And then that is what will give you the best data instead of just sitting around and just talking about it. So we started out with the sitting around attitude, and it's been very hard to get people to be on board with this idea of let's just go do the thing, because I'm not fully convinced. He's not fully convinced. She's not fully convinced. So that's been a very challenging part. I think we're getting better at it, but it's every day we have to be very conscious about sometimes this conversation is not as productive as it seems, and we should just do something and figure it out.
Action produces information. I like that. I think
exactly, yeah.
Definitely a challenge. So I have some rapid-ish fire questions. I'm going to ask you a few. Okay, is there a scenario, and if so, what, in which everything or most of what we're building and focusing on today becomes irrelevant?
Yeah, I think so. I think a lot of people have this in mind of what if just OpenAI and Anthropic build AGI that's good at everything. I don't personally believe in this. I do think the most probable situation is a situation where one that's most similar to where we are right now. The models are really good, but there's so much to do on other sides, like the application layer and infrastructure layer. But I won't deny that I do see, let's call it 1 to 5% odds that OpenAI and Anthropic create AGI and just take the entire market of everything that all other companies are basically doing.
That'd be crazy. So what's one or more common ways that you use AI in your daily life, not professionally?
I use this OpenClaw thing from my phone that basically just counts calories for me. So that's a daily life thing where I just take a picture of my food and it'll automatically, similar to Cal and all these ChatGPT apps. The beautiful thing about this one is that because it's an OpenClaw agent, it'll just remind me to do it and text me and be like, hey, you haven't told me your calories. And that's very useful to me because I'm very forgetful and I always have a lot of stuff to do, as most people do. I don't know, most people are very busy. So yeah, that one's a nice one that came to mind.
That's a good use. What is the most overrated trend in AI right now?
That's a good one. Okay, this might seem counterfactual to the previous answer, but OpenClaw is good, but it's just not there yet. I see it fail out at a lot of things that are serious. Obviously, calorie tracking is a very simple one, and I do think OpenClaw will be a huge market, the personalized agents. So for now, there's more sort of there's more noise around there, then it's hard to find signal into like what are the things that people are actually using OpenClaw for. The ratio of noise to signal is still very, very high.
What is most underrated, do you think?
Man, underrated. I'd say how good agents have gotten at creating documents for proposals, creating like slides, every sort of like presentation and material for your company. If you give it access to like your Figma, if you give it the correct context from like your Granola, your Slack, and you tell it to just like look through it all, you can basically like automate a lot of this stuff that requires a bunch of your time. Like after a meeting, just like the notes and like sending a follow-up. There's like all of these like small productivity gains from having an agent. I just use like Claude for this, nothing fancy. Claude with like all the integrations to Slack, Granola, and everything literally just saves me, I would say, hours a day of just writing documents and all these things that I used to do manually.
It's a good call because I think although a lot of people have access to it now, not everyone is utilizing it to that best ability.
Exactly. And it's worth it to just like add the little integrations, even though it's still annoying, but it's worth it.
What is a project or company that is really inspiring you right now in AI?
Ooh. I'm always really inspired by the chip companies, people building chips to compete with NVIDIA. I'm really inspired with Matx, that's MATX, which recently raised the seed round, and the CEO is one of the original people from the TPU team, extremely smart, Rainer Pope. I've seen a lot of his content. I think he's incredible. I like companies in general that are building chips, as I said, so like Matx, Etched, Furiosa, all these like companies, they're doing something that is just like so freaking hard that I just respect it so much. Cause I'm like, I'm on the softer side and it's like, it already gets hard. I cannot even imagine what it's like to just build a physical device that needs to run these LLMs faster than what NVIDIA is doing.
And what is an underrated project or company in the AI space, in your opinion?
This is a really good one too. Do you know why this question is so hard? Is because with the AI hype, nothing seems underrated. Everyone is just excited about everything. Again, this goes to my personal thing. I'll say one that could be underrated, which is basically grabbing, this is also health stuff, doing some sort of blood tests and putting that into ChatGPT. This is just an application. This is not like a specific tool. But just it's underrated how much health advice and health guidance you can do, and from just using ChatGPT with really good context, and that context being your actual health data, also applies to Aura Rings, Whoops. Like you can just use their MCP, use their API, their CLI to just query this data and have like a dashboard of your health. And in my opinion, have much better tracking of that data than what the apps will give you out of the box.
But yeah, it would be really nice if there was a health product, but I know traditionally that is one of the slower sectors to move with innovation and when it comes to products that people use and interact with.
Yeah.
Cool. Well, that's all I have for today. Do you have any last words or piece of advice for the listeners?
No, I think we had a fun conversation. I don't have much to add.
All right. Well, thank you so much, and thanks for taking the time.
Thank you, Alexa.
Thank you so much for listening to Alexa's Input AI. And if you want to follow along with my new episodes, writing, content, everything I'm building, you can find me at alexagriffith.com, on Substack, on YouTube, or wherever you listen to podcasts. If you enjoyed this conversation, it would mean a lot if you subscribed, shared this episode with a friend, left a quick rating or a comment to help more people to discover the show and keep these conversations going. Again, I'm really grateful you're here. This podcast started as a side project for me a few years ago, and every listener who reaches out or keeps coming back reminds me exactly why I love doing this and I love putting so much time into it. I hope this episode gave you something to think about, something to talk about. So always stay curious, stay grounded, and I hope to see you next time. Thank you for your support.